want to knock out or that we want to modify in some way. And over here on the right, you can see what that looks like in more detail, where when it finds its complement, so it matches all the C's topologies, all the A's topologies, etc., then it'll bind there, and then it has these kind of tiny molecular scissors that actually physically come together and actually cleave the DNA. And that cleavage process can be used in a variety of ways. One way is you can just let it cleave, and then the kind of messy repair of that often you'll knock out the gene. But you can also think about more kind of creative things, like what if you could actually insert a new sequence, or what if you could not cleave anything at all and just kind of leave some sort of epigenetic marker upstream. There's one of the really exciting things you can do once you have this technology that allows you to send a protein anywhere in your genome very reliably. And this is part of just a broader kind of revolution in the biotech space, which is what we call platform technology. It's really important element of CRISPR, compared to anything that came before it, is that programmability. So that idea that you can switch that guide RNA, so that top part on the left here, and you can switch from disease A to disease B without having to re-engineer the whole system. That's been a big part of kind of the CRISPR revolution, and why these technologies caught fire in so many different areas so quickly, is because of that kind of limitless reprogrammability and reliability. So this is a great system. So like, you know, why are we not securing every genetic disease? Well, it is a really great system, and we actually have right here something like disease. But it has a lot of limitations. And one of the biggest ones is a barrier to doing what we call in vivo therapies. These are therapies in the body. But there's other ones as well. You might have heard about this idea of off-target effects. So this is where the CRISPR system is maybe going places you don't want it to go. It's not perfect. Or things like the type of edit. So instead of just cutting it so you can get rid of the gene, what if you did want to insert a paragraph? Or other things, these are more complex techniques that you have to build on top of it. And then there are limitations to where it can target. So like, what if you could actually target any mutation in the genome rather than just targeting a certain subset? These are all areas where you can make really big improvements to these initial CRISPR technologies. And I think the area that's most exciting to me and to Nana as well is that idea of moving from ex vivo therapies to in vivo. And what this means is when we say ex vivo, this is where the editing is going on outside of the body. So you can only do this for certain diseases. So a really good example would be a kind of blood-based disorder, like sickle cell disease, for example. So this is something where you can take the cells out of the body, you can make whatever edits you want, and then you can put them back in. And it's a lot easier, as it turns out, than you might guess, to make edits outside of the body than it is to do inside the body. But if we think about genetic disease, like where is it located? The brain, the heart, the liver, the lung. It's really difficult to rip those out and put it at the back end. It probably wouldn't be great for the patient. So we need a way of doing what we call in vivo editing, which is where you would get a single injection. It would guide the CRISPR technology to the right cells, the brain, muscle, wherever. It would perform the edit, and then it would go away safely. So this would be a revolution in terms of actually tackling the vast majority of genetic disease. But I do want to give credit to the space so far that actually, well, CRISPR is a very sci-fi technology, but it's not sci-fi in the sense that it's actually now an approved therapy for sickle cell disease. It's based on ex vivo CRISPR technique, approved in the here in the United States. Actually, we've approved in the UK before that as well. So this is a really exciting kind of next step for the technology that's already started to prove itself in a very short period of time. CRISPR, the first papers came out of the development lab a little over 10 years ago, and now it's already having approved therapies, which for people in the tech space, it sounds like a long time. But in biotech, that's an extremely rapid advance from something that was a new invention all the way through to. So at Biotech, we have a lot of people who are intimately familiar with this space, including Jennifer, who's one of the co-founders of the company, won the Nobel Prize for her work in CRISPR a few years ago. And then many others in her lab, like Janice and Lucas, and a team of 150 individuals that really been pushing the space forward as well. And what we looked at is like, okay, so CRISPR is this amazing platform, but it passed by the first kind of iteration of this technology has no limitations. But as we saw, this is a technology that comes from nature. So we said, well, nature is different flavors of this. So what we do is we can look at giant databases of what we call metagenomic data. So this is data of just sequencing from all sorts of microbes, whether that's from volcanoes, from soil, from the chair on the stage, anywhere that has hybrids is going to have bacteria or other organisms that have versions of CRISPR. And we can sort through all of that, and we can say, well, there's certain properties we're looking for. Maybe we're looking for the size of the protein, we're looking for the reliability of the edit, we're looking for the locations in the genome that we target. And we can, through applying machine learning techniques and a huge amount of just high throughput experimentation with a bunch of results, just run really high throughput experiments, we can then pull out novel versions of these CRISPR technologies and do a ton of engineering to get them to actually work in human cells. And these new nucleases, things like Cas14, Cas-E, Cas, these are all different flavors of CRISPR that have various properties that can give an advantage over Cas9, which is the original one. So we've been working on this for, well, including my co-founders for over 10 years now. And the real goal here is how do we go towards these permanent cures, which means we have to go in. And in particular, how do we address those limitations I was talking about earlier? Things like the location of the genome target, the type of edit that you're doing, how much you can multiplex, like can you do multiple edits in a cell. And one of the areas that we really focused in on, because it's one of the biggest limitations to actually bringing this technology into our bodies and doing this type of in vivo editing, was the size. And if we look at existing kind of CRISPR technologies like Cas9 and friends, these are actually quite large proteins as these things go. Now, of course, you'll see them in your hand, but they're 1,500 to 1,000 amino acids. And this presents a big problem because a lot of the ways that we deliver these types of payloads in cells are very short size. So one of the fundamental innovations we've been able to do is we've been able to find really, really tiny versions of these CRISPR technologies that just weren't possible previously. So these are things like Cas14, Cas-E, that can be a third or less the size of the original proteins. And you can think of this as kind of like trying to navigate around the city like London. You either have a giant semi-trailer, fairly here on the corner, or you have a little smart car that can just easily get around to different areas. And what we've really been focused on here is then how do we use this with kind of very well validated delivery technologies, things like LP, AAV, where especially AAV is one of the main methods we have to go to tissues in the body that are not the liver. LP is pretty good at the liver. You might learn LP from obviously the pandemic, vaccines. This can also be used to deliver gene editing technologies, but it has its limitations in terms of which tissues it can go to initially go into the liver. So if we want to go beyond the liver, AAV is really the game in town. And here, there's very strict size on it. And actually, the original Cas9, the original CRISPR technologies don't fit at all. But these new smaller versions of CRISPR fit with a ton of room to spare. And when you have that ton of room to spare, you can think very creatively about how to use it. And one of the ways that we're using it is to also build in these kind of new types of edits. So we talked about how you can do double-strand breaks to do like this knockout gene, that's just using the cutting part of this protein. But there's other things you can do as well. You could insert a paragraph. That would be what we call gene writing. That's additional machinery that you need to put into the AAV. Or you could do epigenetic editing. So that's kind of, instead of knocking a gene out, what if you turn a volume knob on the gene, make it louder or softer, depending on what you need. Or base editing. So just change a single letter in that entire document of your genome. These are all techniques that require you not just to deliver the CRISPR protein, but to deliver other machinery as well. So this has been a huge unlock in terms of how do you actually do any type of edit anywhere. So I think the mammoth opportunity here, and what I hope you take away from this, is that we really are on the cusp of being able to do any edit in any cell, which is an incredible innovation for a field that I think we are trying to super messy. And honestly, it is really messy. And I think what this is going to unlock is the ability to potentially permanently cure genetic diseases. And there's 6,000 of them plus that we already know. But what I think is even more exciting is that there's many diseases that we don't even understand about that. And we're rapidly reaching the point where I truly believe we're getting better at editing the genome and changing the good of life than we are even understanding what to change. So the next wave of information will have to be further innovating on how do we actually understand the genetic basis of disease itself. So looking forward to the panel and really excited to kick things off.
And set the stage very well for our next speaker, Wolfgang, who is director at Altos Labs. He is going to ask the question whether it's possible to achieve a cellular reset, that is, can cells and organs be rejuvenated, I'm corrected, and can that be an approach to delivering treatment? What?
Good morning, everyone. Welcome to see you all and looking forward to discussing the exciting question that we have, which we just introduced. So, the question really is, can we go back in time? Now, it's not time travel and get your hopes up too much. It's the question of whether we can look at how our cells age, understand that process better, and run it back to some extent ourselves.